So in our first lesson of homework packet 4.3, we're going to take a look at graphing still, but we've got two new functions that we want to graph. And in this video, we're going to look at the first of those two. We're going to look at graphing polynomial functions. So with all the other function types, we've taken a look at reminding ourselves what the function looks like, and then also taking a look at what it looks like when graphed. So let's remind ourselves what a polynomial is, and then ask the question, what does its graph look like? So here's some examples of polynomials to remind us. Polynomials are quadratics that have higher orders of exponents. We remember a quadratic stops at x squared. We call them polynomials when it continues above an x squared, to the point where you may have an x to the third, or an x to the fourth, or in this second example, an x to the fifth equation. So anything that has an exponent value higher than a 2, we're going to call them polynomials. And all three of these do. This one has a highest exponent value of 4. This second one has a highest exponent value of 5. And this third one has a highest exponent value of 3. So the question then is, what do these look like when we graph them? Well, we've got this chart right here that's going to help us quite a bit. And this chart is called the end behavior chart. But before I fill this out and explain what it's going to help us with, let's first ask the question, what do polynomials look like when graphed? Well, every polynomial has a set of x-intercepts. Okay? And interestingly enough, you've already done the process of how to find the x-intercepts of a polynomial. How do you find the x-intercepts of any equation? You plug 0 in for y. So when you solve this equation for 0, when you solve this equation for x by plugging 0 in for y, do we remember how many solutions we should end up with? If you remember, it's always the value of the highest exponent. So when I plug 0 in for this equation, I expect to get 4 solutions, which if I'm plugging 0 in, what does that mean about these solutions for x? It means that they're x-intercepts because I plugged 0 in for y. So this equation in particular is going to have 4 x-intercepts. This one's going to have 5 x-intercepts. And this one's going to have 3 x-intercepts because those are the largest exponent values respectively for each equation when you set it equal to 0 and solve for x. So let's just say we have an equation that has, let's in our example use 3 x-intercepts. And I don't know where the x-intercepts of this equation are, but let's say they're here, here, and here. What a polynomial equation does is it, with a smooth curve, flows through one x-intercept to the other. A nice smooth curve from one x-intercept to the other. Now it doesn't have to look like that one. In fact, it could have started up here, come through here, nice smooth curve through that x-intercept, turns back around to go smoothly through that x-intercept, turns back around again to go smoothly through that x-intercept. Those are two different options of what it could have looked like. Well, in fact, there's more options even than those. Because sometimes a polynomial doesn't actually have to go through the x-intercept. Sometimes it'll smoothly come up and touch the x-intercept and turn back around. And then maybe it'll come up through this one and then down through this one. But in any case, it's always at least coming and touching an x-intercept or going through the x-intercept smoothly from one to the other. Because it could have done this up here instead, started up, come down and touch this x-intercept, come down and go through that x-intercept, and then smoothly back around through that x-intercept. So there's a lot of different options, but in every single option, we're always connecting with a smooth curve the x-intercepts, whether we just touch them or go through them. Now, the question is, of all those possible solutions, which one is the right one. And that has everything to do with this table that we're going to set up. If you only copy one thing down from this slide in your notes, this is what needs to be copied down. Copy down the end behavior. Okay, I'm going to draw a couple arrows in each of these boxes, indicating something that will point out. Okay, in a graph. Leading coefficient and leading exponent. What that means is you're going to look at the very first term that has the largest exponent value. So this would be then the leading coefficient, that's the number in front of the x. The leading exponent would be a 4. With the coefficient, we care about whether it's positive or negative. And with the exponent, the leading exponent, we care about whether it's an even or an odd. So there's actually 4 different combinations of a positive, negative leading coefficient combined with an even or odd leading exponent. If we have an even leading exponent that's positive, I'm just going to draw 2 arrows going up. We'll see what that means in a moment. If I have a positive leading coefficient with an odd leading exponent, here's how I'm going to write it. It's actually going to be a down arrow, up arrow. Okay. Now back to the even exponent. What if the leading coefficient is negative? I'm going to draw 2 down arrows. And last but not least, again, what if our leading coefficient is negative, but the leading exponent is odd? Well, in that case, I'm going to draw an up arrow and a down arrow. So here's what this means. If we look at this last one as an example, again, I don't know where the x-intercepts are, but let's just assume that they're here, here, and here as I've drawn them. I'm going to look at my leading coefficient and my leading exponent. And I see that my leading coefficient is negative, so I'm here, and my leading exponent is odd. It's a 3, it's odd, so that means I'm here, which means I fit into this category because it's negative and odd. What that means is this is my end behavior. On the left-hand side, I start high, and on the right-hand side, I start low. So to get from here to here, I know I'm going to have to smoothly go through this point, smoothly go through that point, turn around, and smoothly come back down. So these arrows right here tell you where you're going to end, where you start and where you end up after smoothly going through all of the x-intercepts. So let's practice that on a couple examples in the next slides. So here's our first example of graphing a polynomial. Now, as you saw from the previous slide, it's in large part dependent upon where the x-intercepts are. Well, in order to find the x-intercepts, I plug 0 in for y. So I'm going to go 0 equals x to the third minus x squared minus 6x. Let's remind ourselves of how to solve an equation like this. It's solved by factoring. So I'm going to first ask myself, what does each term here have in common? And every term has an x, so I'm going to factor an x out. If I factor an x out of each term, what's left over? If I factor an x out of x to the third, I'm left with x squared. If I factor an x out of negative x squared, I'm left with a negative x. If I factor x out of negative 6x, I'm left with a negative 6. Okay, so we recall doing that from Unit 3 in solving polynomial equations. Now, after identifying what every term has in common, we've factored that out, but now I have this piece left here that is a quadratic. It's an x squared. Okay? And I want to factor that even more. Now, recall, this is an x to the third equation, so how many solutions do we expect to get? We expect to get 3. So let's continue factoring. If I have x squared minus x minus 6, I know that one way I could find the 2 solutions from this remaining piece is with the quadratic formula, but I think I can much more quickly find it by factoring. I know I put an x and an x here because x and x is x squared. But then what two numbers multiply to -6 and add to -1? And I believe that that is going to be a -3 and a +2. Yep, -3 times 2 is -6, -3 plus 2 is -1. I still have this x out front. So again, we expect to get 3 solutions because it's an x to the 3rd equation. So what are my solutions? Well, I've got 3 pieces here equal to 0. What value can I plug into x to make x 0? Now that's a 0. What value can I plug into x that makes x minus 3 0? That would be a 3. What value of x can I plug into x here that makes x plus 2 equal to 0? That would be a -2. So what I've found right here is my 3 x-intercepts. I found that they are at 0, +3, and -2. So I know those are the points that I travel through. Okay. Now, I mentioned in the previous slide that sometimes you can just touch an x-intercept instead of pass through it. In this case, we're going to actually pass through all of them. I'll show you what situation happens which causes us to just touch an exponent in the next example. Okay. So 0, 3, -2. Now from the previous slide we had that chart with end behavior. If you recall, if your leading coefficient is positive, right here we have an implied 1 in front of the x to the 3rd. So I have a positive leading coefficient and an odd leading exponent. I believe, if I remember correctly, that that goes from down to up. So I know that I start down here and I end up here. Well, I think that I can smoothly connect and go through my x-intercepts very nicely and follow that end behavior. And there it is. There's the graph. Now, don't worry about how high or low you go between each of them. Just make sure that you have the correct end behavior. You're starting and ending where you're supposed to, and that your graph smoothly goes through and curves through all of the identified x-intercepts. So on your graph, the only thing I need you to label are the x-intercepts, -2, 0, 0, 0, and 3, 0. And there's the graph of this polynomial. So let's continue with this next example. We've got f of x equals -2x to the 4th minus 2x to the 3rd plus 24x squared. Now we remember from the previous example that the first thing we need to find if we are supposed to graph a polynomial is to find the x-intercepts. How do we find the x-intercepts? By plugging 0 in for y. So 0 is equal to -2x to the 4th minus 2x to the 3rd plus 24x squared. Now in solving this for x by plugging 0 in for y, how many solutions do I expect to get? I expect to get 4 solutions because it's an x to the 4th equation. So let's factor this by first asking ourselves, what does each term have in common? I see that each term has a -2 that I could divide out of it. And I also see that each term has an x squared that I could divide out of it. Now when I say divide, I actually mean factor. But how do you factor something out? Through division. So let's divide -2x squared out of -2x to the 4th. That leaves me with x squared. Let's factor out -2x squared from -2x to the 3rd. That actually leaves me with a plus x, because a negative out of a negative switches to a positive. And then let's factor -2x squared out of 24x squared. And I believe that leaves me with a -12. So I've got this piece here that I factored out, and then I've got my remaining quadratic. Right? So let's continue to factor that remaining quadratic. It's an x squared, so I know I do x and x. So now I have to ask myself, what two numbers multiply to -12 and add to a 1. There's a 1 right there. So if I think about it, work through any process that I need to, I think what I'm going to find is that the two numbers that multiply to negative 12 and add to 1 are a positive 4 and a negative 3. Let's see, 4 times negative 3, yeah, it's negative 12. And then 4 plus negative 3 is indeed a 1. So 0 is equal to negative 2x squared times x plus 4 times x minus 3. So the question that we are then left with asking is, what then are the solutions now that I've put it in factored form? Well, I ask myself, what makes each part equal to 0? Well, if I plug 0 into x minus 3, what do I plug into x to make x minus 3 equal to 0 is what I meant to say. And I know that's a 3, so x equals 3 is a solution. What can I plug into x to make x plus 4 equal to 0? I can plug in a negative 4. Lastly, what could I plug into x to make negative 2x squared equal to 0? Well, I could plug in a 0, because 0 squared is 0 times negative 2 is 0. Now here's the problem. We knew we were supposed to get 4 solutions. I only have 3 right here. However, if we remember multiplicity, we remember that if it comes from an x squared, that it has a multiplicity of 2. That's going to come into play in just a minute. So we just found that our x-intercepts are at positive 3, negative 4, and 0. So those are the points I know that my graph is either going to go through or touch. So what about end behavior? If we remember from the chart, we look at the leading term. My leading coefficient is negative, and my leading exponent is even. If I recall correctly, I believe that means that I start down and I end down. I believe that means down, down. So I know that I start down here and I end down here. So if I start down here, I can come up and through this x-intercept, back down through this x-intercept, and back up through this x-intercept. Here's the problem. I just ended up. Where am I supposed to end up? I'm supposed to end up down. So the problem is this idea of multiplicity. Right here, x equals 0 has a multiplicity of 2. That's this x-intercept right here. What is unique about that is this. If an x-intercept has a multiplicity of 2, the graph doesn't actually go through that point, it just touches that point. So watch what happens. I know I have to start down, I come up and through this x-intercept, but I know that I cannot go through this x-intercept because it has a multiplicity of 2. I'm just going to touch it and bounce right back off, but then I have to turn around again to make sure I come through that x-intercept, and look at that, I end up down just like the end behavior said that I should. So here then is the graph of this polynomial, labeling the x-intercepts negative 4, 0, 0, 0, and 3, 0. And there's the graph of this polynomial equation.